Notes. All right, so anything that's printed, you can bring. Yeah, yeah. So bring your entire notebook, all the packets that I've given you. The only thing, you probably shouldn't do, but although I don't know how I would know, is you probably don't want to go on my website and print out all my completed notes and bring that, just because they're not your notes. They're my notes, so I would understand them beautifully. You, I mean, you'd be trying to not only interpret what's written there, but interpret my thinking and why I would write it. If you use your own notes, then at least you're interpreting your own thinking. All right. So, with that in mind, I can tell you from personal experience that open notes tests can be very dangerous, which is why I kind of keep it in the bag as long as I possibly can. And I kind of let it slip here and there, but I try not to advertise it too early on, because what some folks do, and this is not an indictment on everyone, it's just an indictment on the one or two people who would do this, and that is, oh, it's open notes, so I'm not going to study. Be fine. Everything will work out. And then you go into the test and you're seeing everything for the first time. And it's like, yeah, you found the pages in your notes that are relevant to the problem, but you can't even decode what's written on the paper. Because our ref, cool, we do that a lot, but why did we do it in that context? Why is that important there? You know what I'm saying? So tried to keep you on board as long as possible, but at some point I had to make it official and say it is in fact an open notes test. Yeah. So anything that I've given you throughout the course, handouts, old tests, anything short of technology is going to be fair game. Obviously a calculator's allowed, but like anything short of actually whipping out a laptop and opening up GeoGebra, is generally going to be considered okay. If you're unsure if what you're considering bringing is going to be fair game, message me. It's not what it's. Let's just put it this way: it's not one of those things where it's better to apologize after than to ask permission before. This is not that. All right, you don't want to find out the day of, oh, I can't use this. Well, I was banking on being able to use this. If you're not sure, just ask. All right. So that should help alleviate things a little bit, and also give you a fighting chance to kind of get through this, possibly with even like Thursday being the unofficial last day for you. It could be the official last day, because we do have a unit circle quiz next week on Tuesday. But what some folks have opted to do in the past, I always bring the unit circle quizzes with me the day of the last test. They say, listen, I think I'm going to be in a pretty good position to not have to take the final. I meet the attendance requirement, because that's the thing that you have to meet in order to drop the lowest test grade. Some people are shocked by that at this stage, although you shouldn't be. If you meet the attendance requirement and you think that you're where you need to be, then after you're finished with the test, just say, hey, I have one of those unit circles, crank it out on Thursday, and then maybe we're saying goodbye to each other Thursday evening, like for the course. Okay, so this last test should be pretty easy to grade anyway. So I might even be able to crank it all out and let you know where you stand before you even leave the room. Small enough class. If this was one of those 35 person classes, I wouldn't make that promise. But when you're looking at 11 students in a class, that I could probably crank it all out. Right. So at a minimum, you'll have a sense of where you're standing going into the final. So if you need to take that final, you'll know by Thursday. If you don't need to know, that's the better news, obviously. You'll know that also. All right. So hopefully that makes sense. Oh, I talked about that for 4.5 minutes. Cool. All right. So the last topic. So the new handout that I gave out. Did I get everyone? Did you get one? Yeah. So partial derivatives. I streamlined it big time because what are we going to do in one class? And I didn't want to rush other components of it. That in the packet that I gave you prior to this, it was a lot more of the formulation of where a lot of this stuff is coming from, not so much the implementation. So like we're just going to get into the rules of how to find a tangent plane, not so much what, the origin story behind the tangent plane. All right. So partial derivatives, very straightforward concept, at least in and of itself. How it can be expanded upon and the intricacies of it, like it's like taking derivatives in a Calc 2 course, or antiderivatives. It's as easy or as difficult as the function. So if you had some kind of transcendental function with two inner components, it could be hard, but the concept of U substitution, for example, is not difficult. It's just the types of problems that could be thrown your way could be challenging. This is the same idea, but even with that in mind, we're still going to keep it fairly basic because, again, not a Calc 3 course, right? So if you haven't taken a Calc 3 course, this would be a little taste of something that you could expect to see. All right. So partial derivatives are really just holding one variable constant while taking the derivative of another. That's assuming it's a function of two variables. If it's a function of 10 variables, you'd be holding 9 of those variables constant and taking the derivative with respect to the 10th one. All right. And then, possibly doing it with respect to each one of those 10 variables. So obviously it could get a little out of hand very quickly. All right. But what we're going to do here is just focus on functions of two variables. All right. And then just kind of get into it a little bit. All right. So, there's a limit definition related to each one of these. But if you remember from Calc 1, the concept of a limit definition of a derivative, like actually finding the derivative using the limit definition, it didn't really bring anything to the party. Right? It was kind of more an exercise in your ability to find limits and evaluate limits, more so than your ability to actually understand where the derivative is coming from. We know that the limit definition of a derivative is really just telling us the instantaneous slope over an interval, a very teensy tiny interval, but it's still an interval, all right? Because we're saying h is some infinitesimal change horizontally, for example. What would happen in terms of the vertical change, all right? Same idea if you were to do it in terms of y, right? What this is telling us is that we're establishing, when we're taking the partial derivative of that funky d, which is really a lowercase delta, that partial derivative of the function with respect to x, we're finding the infinitesimal change in x, but we're leaving y alone. Y is remaining unchanged. We're treating y as constant. Right? In the case of taking the partial with respect to y, we're leaving the x alone and finding that infinitesimal change in terms of y. Right? So all that's saying is what I was saying before, treat one variable as constant, differentiate with respect to the other. All right, so in the case of number 1, now go back to Calc 1. If it said find the derivative of this, you'd have to use implicit differentiation. This question would be like the definition of a nightmare, right? Because you'd have, you got to treat each component as variable. So what that would mean is that the first two parts would be fine, but then you'd have two product rules built in there. Horrible. But that's not this. What we're going to do is find the partial with respect to x of x, of the, your function in terms of xy. So it's telling me, undo. It's telling me to treat x as the only variable. Poor quality arrow. And I'm putting variable in quotes because they're both variables. I'm just only allowing one to vary, right? So, and that's an important thing. Yeah, you got the new one?
Oh, is it different from this one?
Yeah, it's a more streamlined one.
Ah, okay.
And remove the typo
Thanks.
or two. All right, so I'm only allowing x to vary. I'm treating y as constant. All right, so in the case of 3x squared, my derivative there would be just 6x. So I'm going to take the derivative of that the way I normally would. For my second piece, well, there's no x there, so I'm not allowing anything to vary. So what would my derivative of 4y squared be? 0. Because 4 itself is a constant multiplier. The y squared I'm treating as constant. So a constant times a constant is a constant. And if I say the derivative of a constant all the way back to Calc 1, hopefully you say 0. All right? Now, the next one, a little bit different because it's got both quote-unquote variables in there. But what I'm going to do is I'm going to rewrite this as negative 2y times x squared. Now, you don't always have to rewrite it, but at least this one time I'm going to do it. All right, because really what we're doing is considering that negative 2y as the constant multiple of x squared. All right. Try to make that look more like a multiplication symbol, but as I try to adjust it, it just keeps looking more and more like a minus sign. All right, so the negative 2y is the coefficient of x squared. All right, so power rule. Multiply the power by the coefficient and reduce the power by 1. So negative 4y x to the first power. The next piece I could think of as 7y squared as a coefficient of x. All right, now that x could be thought of as x to the first. All right, so it's going right back to a times b to the, a times x to the b power. All right, so the power rule for derivatives. Multiply power by coefficient, reduce the power by 1. That 7y squared is the coefficient. So when I multiply that by the 1, I'm going to get 7y squared. Times x to the 0th, but x to the 0th is going to 1 anyway. All right, and then the negative 9 is going to 0 because the derivative of a constant is equal to 0. All right, so I'm looking at 6x minus 4yx plus 7y squared. And so that's my partial derivative with respect to x. All right, so what that's telling me, again, is that if I'm holding y constant, this is going to be a function that represents the change in the z, because when you have a function of x, y, it's equal to some function z. Right? So the rate of change of z in terms of x. All right? So what you have to actually imagine is, and imagination is part of the fun here, I guess, because otherwise it's GeoGebra. You have some three-dimensional surface, because f of x, just how f of x was y equals, f of x comma y is z equals. All right? So you can make a note of that. So you could say same as z. I'm just making up spellings here. Same as z. So this is some z equation in 3 dimensions. All right. So when we talked about writing the equation of a plane, we put it in GeoGebra. Z equals. You could have some 3-dimensional surface, something like this. Z equals all of this stuff. This, I don't know what it looks like, right? It's some sort of quadric function, some sort of conic section just in 3 dimensions. So a variation of an ellipsoid, so basically like a big football in space, all right? And that's only because these coefficients are both positive. I'm sorry, the same sign. It doesn't matter what sign they are as long as they're the same. But the bottom line is, this is some figure that's floating around in space. What this is telling me is that if I chop this with a particular plane going through a y, you know, like y equals 2. So create a plane going through y equals 2. It'd have to be parallel to the xz plane, right? So you have the xz plane, you have the y-axis coming off this way. Chop it through the surface with some plane, you create a cross-section. On that cross-section, the outer edges of that cross-section, you could then decompose that into basically some function that you could look at in 2 dimensions, right? So if you think back to conic sections in pre-calc, you know, if you were to take an ellipsoid, so a football, and chop it, you know, depending on how you chop it, you're going to get some variation of an ellipse. You might get a circle if you go right down the middle, actually at any point, but if you go on an angle, you're going to get an ellipse, right? So what's going to happen here is you're going to get some 2-dimensional figure just by chopping it along some y equals plane, right? And what that does is it allows us to use our 2-dimensional knowledge of calculus to evaluate, right? So now I have a function in 2 variables, but again, depending on what my y value is, this is going to be linear, right? Because let's say I'm holding y constant at 1. Actually, I'll make it even simpler. I'm holding y at 0, which means it's the xz plane, right? I'm looking at a linear relationship, just 6x. Z equals 6x. I now know what the relationship is between x and z. For each change in x, I have a 6-unit change in z, right? Because it's linear, right? So you can determine a lot of things, but the one drawback is, well, what if you wanted to vary in both x and y? Well, okay, so you do that, but now what we have to do is we'd have to say, okay, well, let me hold the x constant and look at it from the perspective of y. And so that's what the next one would be. All right, so I'm going to write it as partial f with respect to y, not x. But I'm not going to write of xy. All right, so we streamline it a little bit. But now anywhere that it's just strictly either a constant or strictly in terms of x, those are going to go to 0 and we could ignore those. All right. This guy right here is a y function. Take the derivative of that the way we normally would, because we're treating the y as the only variable. I hate when that happens. All right, so any x would be treated as constant or a constant multiple. All right, so 4y squared becomes 8y. These are, we don't even actually have to rewrite these because they have the x terms or the x factors coming first. So this is something y to the first power. So using our power rule, it's really just a matter of saying, all right, well, 1 times negative 2x squared would be negative 2x squared. Y to the 0th, so get rid of that. And then for the other piece, 2 times 7x, 14x, reduce the power by 1, so you'd have a y. All right, so that would be my, well, they call it a first order partial with respect to y. Because you could have what are known as second order partials, which are basically second derivatives. But then it becomes a question of, am I going to do it with respect to x or with respect to y? And then a question of, well, which one am I starting with? Am I treating this as my first derivative or am I treating this as my first derivative? So actually, as it turns out, there's 4 second order partial derivatives. All right, you have with respect to x and then with respect to x again, with respect to x and then with respect to y, with respect to y and then y again, y with respect to x afterwards. All right, but we only need to worry about the first order partials for what we need to do here. Okay. Could also incorporate trig functions. You'll notice in the previous version of this packet, I had a little investigation involving cylindrical and spherical coordinates. It would have been a cool application, but we just don't have the time for it. So, for an optional topic to begin with, I didn't want to opt into rushing the optional topic. All right, but if you look at a problem like this, again, back to Calc 1, pretty nasty. Product rule, exponentially. And, nasty is relative, I guess. For a first-time calculus student, learning about product rule and implicit differentiation, nasty. All right, if you have a lot of experience with it, maybe not so much. But here, there's nothing to it. All right, because our variable, our relevant variable, is just the x. All right, so undo. This sine of y is really just a coefficient. It's a coefficient of the cosine of x. The only thing I need to actually take the derivative of is the cosine of x. That sine of y is just coming along for the ride. So sine of y times the derivative of the cosine of x, which is negative sine x. So let me just tuck in the negative in front. Save myself a simplification step. So negative sine of x, as you said. All right. Now for the second piece, this is the only real twist or iffy part of this. When you take the derivative of a function that's in terms of two variables, sometimes you could just let one be the coefficient of the other, but sometimes there's going to be chain rule involved no matter how you slice it, right? Because this is an exponential e raised to a power. Whenever you take the derivative of exponential e, it's always the exponential e itself multiplied by the derivative of the exponent. All right, so in my exponent, I have an x as the relevant variable, but the y is treated as a coefficient of x. All right, so this y is just treated as a constant multiple of x. All right. So my derivative just of xy would be what? Just the y, yeah. Yeah, it would be y e to the xy, exactly. Yeah, when you put it all together. Now, if we had to do a second order partial, this could get a little crazier. Right, because let's say I needed to do this derivative again, but now I have to use, the second order partial with respect to y. Now I have, the first part won't really be any more challenging, but the second part, I'm looking at two factors of a product, each containing a y. So I have to incorporate product. Right. Now, if I'm doing it with respect to x, then this is just treated as a coefficient anyway. So it's not going to add any level of difficulty. Right? But again, I'm talking about something you don't have to worry about, but it's something where if you haven't taken Calc 3 yet, and you need to, you're going to be on a hook for it at some point. So the earlier you try to start to understand that kind of stuff, the easier things are going to be. All right. I guess I could say that about a lot of things. Partial with respect to y. So I'm treating all of my x's, anything involving an x, as a coefficient. And now anything that is in terms of y, I'm going to treat as variable. All right, so coefficient, cosine of x is just going to come along for the ride. The derivative of sine of y is cosine of y. All right, so same logic behind the derivative of e to the xy. You rewrite Derivative is e to the xy, but then we also need to multiply by the derivative of the exponent. But again, part of it will be treated as constant, as a coefficient. That's this guy right here. And the other part is the variable part. That is not... Yeah, multiply by x, exactly. Yeah, so, conceptually, like I said, not that bad. Strictly dependent on the difficulty level of the functions given. Right? Because you could look at just a comparison between 1 and 2 versus 3 and 4, and you could immediately see the difference. And so it might be as simple as, oh, we have to know the derivative of e functions? Crap, I don't remember that. Well, I mean, I guess that's part of it, but it's more so the idea of knowing that you're holding one variable constant. That's really the moral of the story. All right. So on the next page, we get into tangent planes, which is one of the reasons why we just learned about that. Because in two-dimensional space, you have tangent lines, right? Because, slope of the line tangent to the curve. But then you start getting into three-dimensional space, and what we generally want is something known as a gradient. So, and this kind of works along those lines. This is going to give us the gradient of the plane tangent to the surface. All right, so we're basically upping the dimensions pretty consistently. So you had a line, which is really just a one-dimensional figure, giving you a sense of what the slope would be for a two-dimensional figure. All right? And then you have the plane, which is really just 2 dimensions because it's infinitesimal width, giving us a sense of a three-dimensional figure. Right? So it's scaling us down in one way or another. And you could kind of see how a derivative really supports that. Right? It's just that, when you start thinking about lines, you don't necessarily, you're plotting in a two-dimensional plane, but you're really plotting something that's one-dimensional in a two-dimensional plane. Okay, so the thickness of the line is really, like when you draw that line, you're only drawing it with thickness in order to make it visible, but it's just like the profile of a plane is not visible, right? It's one of those things where, if you look at a plane, in an oblique sense, you could see the surface of the plane, but if you look at it dead on, if it's truly an accurate rendering of a plane, you shouldn't be able to see anything, right? Because if you're going to perceive something in 3 dimensions that's 2-dimensional, how's that going to work? So yeah, anyway, but this relies on partials. And so you can see here that you have the concept boiling down to this lovely looking formula. It's just beautiful. It's stunning, really. If I tell you that f sub x represents the partial with respect to x, that starts to make things a little bit more understandable. All right, so this is the alternate notation. This means the same thing as partial, and I'll write z just to keep it a little bit more concise. Partial z with respect to x. And this one would be the partial z with respect to y. They mean the same thing. Now we learned when we were discussing how to write the equation of planes a while ago, way back when, that a plane is defined based off of its normal line, right? So, or the normal vector. So we could also write the equation of a normal line. That's more FYI stuff, because we're not actually going to do that. But I figure, one goes along with the other, so I might as well just throw it in there. So I'll just write FYI here. So that concept won't be on any assessment. But it's nice to know, I guess. So the first example here looks like a nightmare. Find the equation of a tangent plane and normal line. We'll get rid of that and normal line part. That's the equation of a tangent plane to the surface for x and y values of 1, 1, 1, 0, 0, 1, and 0, 0. That's crazy talk. That's really not that bad. So anytime you incorporate zeros and ones, things tend to get a little nice. All right, so first thing we're going to do is find the partial with respect to x. And then the partial with respect to y. When we take the derivative, regardless of what the relevant variable is, that one's going away. One's constant, whether it's with respect to x, y, z, or... I guess, unless it's with respect to 1. Yeah, because then it would just be a 1. That would be the only exception. All right, so in the first case, I'm treating the x as my variable. That is not a highlighter. So I'm going to take the derivative of just the x squared term, giving me a 2x, and I'm going to bring along the y squared for the ride. Doesn't matter where you put it. It seems to make sense to put it towards the end, though, because it's got a higher power. In the second, and that's it. That's the partial with respect to x there. So, like I said, this stuff is as easy or as difficult as the function you're given. In the second case, we're taking the partial with respect to y. So here's my variable. So I'm going to leave the x squared alone and take the derivative of just the y term. So y squared has a derivative of 2y, so I'll put the 2 in the front just to keep it clean, and the y in the back. As long as there's a 2 and a y in there somewhere, doesn't matter where they are. All right, so we'll start off with the x, y equals 1, 1. All right, now if you look at the formula, and again, like there's a whole origin story behind this formula. I have a completed activity that I can post. I'll post it on my website just so you can see. It involves cross products, and it's really kind of cool. It kind of brings together a lot of the stuff we were learning throughout the course. It's just it's lengthy. That in and of itself would have taken the whole class, so it just couldn't happen. Right? But it explains where this came from, so I'll make sure I post that. But if I'm working with x, y equals 1, 1, it's really x, y at a, b. So we're establishing that the a value is 1 and the b value is 1, if I can properly write a b. All right, so I just need these other ingredients. I need f of ab, partial at ab with respect to x, partial at ab with respect to y. I already have those pieces of information. I just got to do some plugging and chugging. So all the calculus is over. All right, so I need f of ab, so f of 1, 1, partial with respect to x at 1, 1, partial with respect to y at 1, 1. So f of 1, 1 would be what you would get if you replace the z, or the x and y in the z function with 1, 1. Right? Because again, just like on the previous page, where we replaced f of x comma y with z, we could replace z with f of x comma y. They mean the same thing. They're interchangeable. All right. So plug in a 1 for x, a 1 for y, and you're going to get a 2. I'll just write it out. 1 squared times 1 squared plus 1. So 1 times 1 is 1, plus 1 is 2. All right. Then we're going to do the same thing into my first order partial with respect to x. So again, this whole thing here is the same as saying f sub x, and this one is the same as saying f sub y. So 2 times 1 squared, also 2. And then 2 times 1 squared times 1, you guessed it, 2 again. And turned off. All right, so now it's just popping it into our function there. Z equals f of AB. So Z equals 2 plus first order partial with respect to x at 1, 1 is also 2 times x minus the a value, which is 1. And then really the same thing for the next one also. Plus 2 times y minus 1. Now you could clean this up if you want, but that's not really the point behind this. What we want is something that we know is equivalent to the equation of the tangent plane, and that's what we have here. That comes from this rule. I'm just replacing. All right. So I have my tangent plane. If I simplify this down, things clean up a little bit. Like this 2 would cancel with that 2. I'd have a 2x plus 2y minus 2, I think. It's not really important what it simplifies down to. It's just that you have something that you know is equivalent to a tangent plane. All right. And what a tangent plane does is it gives us a sense not only of, just the overall gradient of the function at a location, but it gives us more of a sense of the behavior around a certain point on a graph. Right. So what are the points that are very close to that point of tangency? What are they behaving like as you travel out in different directions? It's kind of weird to think of it that way, but in two-dimensional calculus, it's like, well, you're either going up or you're going down. All right, well, what if you're going up and down at the same time? How could that happen? Well, depends on the surface. If you have something that's kind of bowing in, and then as you go in another direction, it's bowing back up, or maybe even continuing down, you could have something that changes its direction completely, or changes its entire look completely just by going in a different direction three-dimensionally, right? If it's just a matter of like, point me in a direction and just ask me to describe what's happening as I walk in that straight line direction, all right, yeah, I'm either walking flat, up, or down. All right, but how many times have you walked on an uneven surface, and as you're walking in that straight direction, uphill, downhill, or even flat ways, your feet are rocking, like you're trying to walk along, you're hiking, and you hit a root, and you almost roll an ankle. You're rolling an ankle because it does matter what the behavior is of the gradient as you go out in every single direction from that point, not just the forwards and backwards. Yeah, you got to know what's going on in front of you. You don't want to trip over something that's obvious. But if you hit a root the wrong way, you blow an ankle. And I've done that enough. So this is the beginnings of the understandings of the physical manifestation of that sort of thing. Right. So with 1, 0, now this we could streamline this significantly. Because it's like, typo, you didn't give us enough room. Actually, shockingly, I gave the exact appropriate amount of room. Because 1, 0 tells me that the b value is going to be 0, which means everywhere I have a y, it's going to zero out. So both of my partials are going to go to 0. All right. So then the only thing I would actually care about is what f of 1, 0 would be. All right, f of 1, 0 is going to be equal to 1. Right? Because my first order partials, those are both going to 0. Right? Both of them have a factor of y, and y is 0. So everything after this plus sign is zeroing out, irrelevant. So the only thing I would care about in order to write the tangent plane is what the y or the z value is of the function, and that would give me a tangent plane at z equals 1. If xy is equal to 0, 1, in my partials everywhere I have an x, I'm replacing them with zeros. So they're both going to zero out again. I'm going to get the same result when I plug a 0 and 1 in for x and y here. That whole first set of factors are going to zero out. So therefore, this is also going to have a tangent plane at 0, at z equals 1. And then the last possibility would be xy equals 0, 0. Same deal. If I plug zeros in for both x and y here, zeros out, I'm only left with a 1. These are zeroing out, so they're irrelevant. So my tangent plane here would be just z equals 1. So 3 different locations along this graph have tangent planes that, for lack of a better word, would be horizontal. And we only say horizontal because that's our perspective. We tend to think of the xy plane as the floor, and anything that's parallel to that would therefore be horizontal, right? So each one of these, if z equals some constant, the z's height is not changing, right? So I'm looking at 3 different locations along this surface where the horizontal, or where the tangent plane is horizontal, which could lead to, going back to Calc 1, those critical points and things like that. It gives us turning points, right? But what kind of turning point, right? Because you could have a turning point where it seems to be maximizing as you come in from this direction, but then it could be a minimum as it comes in from this direction, right? So you could have 2 different perspectives giving you 2 different realities. All right, one of them gives you a maximum, one gives you a minimum. If it's some kind of contradiction like that, you would just say it's a saddle point, right? But if it gives you a clear maximum from all different directions, then you would call it a local max, and a clear minimum from all directions, you'd call that a local min. All right? But this is the beginnings of being able to handle something like that. That was the first part.
Why you choose the first one? Why you just choose like any one of them?
Oh, well, I did all 4 of them.
Oh, yeah.
So here's the 1, 1, 1, 0, 0, 1, 0, 0. So it had to happen. It's just a matter of which way you wanted to do it, or which order, I mean. The next one's a little bit more straightforward because there's only 2 points that we care about. You look at the cosine function and say, that's going to be nasty. All right, but again, it's partial derivatives, not implicit differentiation. So my partial with respect to x, it's chain rule. So this I'm going to rewrite as cosine of x squared plus y squared to the 1/2 power as soon as I can get my pen to work. I'm just chucking the 1/2 in there. So cosine becomes negative sine. Keep the inner function the way it is. And you could go back to the radical for that. I just rewrote it so that it's easier to take the derivative on the inside with the chain rule. Which is going to be 1/2 x squared plus y squared to the negative 1/2 times this one's with respect to x. So the y component is treated as constant, So I only need the derivative of the x component, so just 2x. All right. Then our partial with respect to y. Literally exactly the same all the way up to the last part. Cosine becomes negative sine. Derivative of the inner function, but this time I wanted to take the derivative just of the y component, which is just going to be 2y. Now, if the thought of, like, I thought you said this wasn't going to be that bad is rolling around in your mind, I respect that. It's still, I promise you, it's not going to be that bad. So first I want to work with xy equals pi comma 0. Got to do both. Here's my a value. Here's my b value. So I'm just going to replace my x's with pi and my y's with 0. All right, so partial with respect to x at pi comma 0, and then partial with respect to y at pi comma 0. Just rolled onto my elbow. I mean, you can look at all this stuff here. We'll get there if we need to. If I plug in a pi for x, I get pi squared, right? Plus 0 squared is just going to ultimately end up being a pi squared under a radical. Square root of pi squared is what? Pi, right? What's the sign of pi? Yeah, 0. Sine of pi is equal to 0. 0 times, you can figure out what all this is going to be. Unless all of this amounts, this component here amounts to 0 also, it's going to be 0, right? So both partials are equal to 0. So then I just need f of pi comma 0. That goes right back to the original function. Right? So since we know the square root of x squared plus y squared, if x and y are pi and 0 respectively, it's going to amount to, instead of sine of pi, it's going to be cosine of pi. What is the cosine of pi?
It's
-1. All right? So just like the last 3 parts of the previous question, the component of the tangent plane formula that involves the partial is going to 0 out. So my tangent plane is going to be z equals -1. So another one of those quote-unquote horizontal tangent planes. All right. Now, if we do it at 0, 0, little bit of a different story. I'll just draw a vertical line. All right, we're still working off of the same partials. So I could use the same notation. I'm just going to put 0, 0 in here instead of pi 0. Well, 0 squared plus 0 squared is 0. Sine of 0 is? My plan of quizzing you on unit circles has not worked the way I had intended. 0. All right, so we know that this whole part is going to zero out. We know that this is going to zero out. The issue here is we have a negative exponent. All right, this negative exponent is telling me that really this whole component here and also here, those are denominators of fractions. All right. So if I plug in zeros for here, I'm going to get 0 to the negative 1/2 power, which is going to put 0 on the bottom of my fraction. In both of these cases, indeterminate. I'm going to get 0 over 0, which is indeterminate. Right, which is the special case of being undefined. All right, it's just the case where on the top value is also 0, not just the bottom to the top as well. All right, so how are you going to write a tangent plane equation with that information? Well, the short answer would be not with this technique. All right, so we would not be using this technique. We would not be able to write the tangent plane equation because you can't substitute a 0 over 0 in for the partial derivative with respect to x or y. All right, regardless of what it's getting multiplied by, it's still gonna, and you know the worst part is, at 0, 0, I'm sorry, no, pi 0 is a different, no, I was gonna say, at 0, 0, you can't even tell what's going on in the picture. It looks like there's a little hump here, which would make you think there's a relative extrema, but it's definitely not happening at 0, 0, right? Because that looks like it's higher. Because that's, I mean, if I'm reading my scale correctly, that looks like 2, so this would be 1. So 0, 1, sure. But at 0, 0, and maybe there's something going on in there, but it's not like you could see from the picture, right? So, unable to write the equation of the tangent plane, so therefore not possible. With this technique. Yeah. I was just doing a quick double check to make sure it was possible, period. Yeah, because 0, 0, yeah, if you plug 0, 0 in here, you get a 1. It is possible to get a tangent plane there, but not based off of this technique. You'd have to use some other method, right? But if you wanted to determine extrema, there is a way to do it. And it seems like the equation of a tangent plane at extrema is going to be in the form of z equals some constant a. Right. But this is a, yeah, I don't want to get too Calc 3 on you here, but if you find the first order partials and they're both equal to 0 and they're both equal to each other, that's how you go about finding critical values. Then those critical values may or may not lead to what we call extreme values. All right, so it could be the case that they give you relative extrema, but they could give you the saddle points, the ones that seem like they're maximums from one direction, but it turns out that they're minimums from another direction. There's a conflict. All right, so that's, yeah, I mean, I'm sure if you go on YouTube, I'm sure you'll find much briefer crash courses on partial derivatives than that, like an hour I gave you, but that is as crash coursey as it gets in a classroom, I think, right? Because we needed that in order to understand what a Jacobian matrix is. So Well, you have to imagine. There's a lot of imagining going on here, by the way. Irrelevant. What you'd have to imagine is that you have a tangent plane at a point, and you're taking infinitesimal steps in any direction from that point. Right? It goes back to linearization from Calc 1, where you had a tangent line, and you took infinitesimal steps away from that point of tangency. You could use that tangent line to approximate the function, but only so far, because the further you got away from that point of tangency, the less accurate you were. Right? Same thing is true with tangent planes. What we could do is use the Jacobian matrix to help us make a determination of what's going on in what they say in the neighborhood of a particular point. All right? But the thing that's beautiful about a Jacobian, or a Jacobian matrix, because the Jacobian is something else, is that we can define it for all variables within any number of functions. All right? So if your function is defined in terms of 10 variables, a Jacobian matrix will capture every attribute of what's going on in the immediate surroundings of a particular point on a surface, right? So the most powerful aspect of that is it's not just limited to 3 dimensions. You can get into the 13th dimension if you want, all right? So basically what a Jacobian matrix is a matrix that consists of all partial derivatives of a given set of functions. So you understand why we needed to know about partial derivatives. Now, what a Jacobian is, it's a shorthand way of saying the determinant of a Jacobian matrix. All right, what that gives us is a measure of the behavior in that general vicinity. Right. Sometimes it's a simple value or a set of values, but what it'll do is it'll tell us whether a surface is maintaining its orientation, or if it's reversing its orientation, or if there's extrema. All right, because again, like I said before, in 2 dimensions, you have a max, you have a min, maybe you have an inflection point. I mean, I found in Calc 1, it was like, all right, yeah, I'm going to find the derivative, set it equal to 0 because you told me to. But I'm also going to look on the calculator to see where the graph is turning. And that's going to be my relative max or min. You know? And then at least I knew what to aim for. But then you get into 3 dimensions, and you got to trust my hand waving. But like, I got a max coming from this direction that corresponds to a min coming from that direction. What does that look like? You know, so you got to kind of imagining that it's increasing from one direction and then making, a right-hand turn and then increasing in that direction, whatever the direction is. So it's a maximum from this path, but a min from that path. And then, it kind of levels off here and then increases on this side while decreasing on that side. I mean, if you ski, you know what I'm talking about. Right, because I just see Gore Mountain. Right, you get up to that first lift. It's my first lift. Right, so you ski down, and you could ski all the way down to the bottom of that particular part of the mountain, or you could grab a chairlift and go up to the top of the next mountain. Right, so it's definitely a saddle point as you're working your way down. It levels off and then it continues down. But from the perspective of looking at the chairlift going up to the top of the next mountain, it's a minimum point, right? So it's really just a matter of visualizing terrain. If you could do that, then you have a sense of what these things would look like in 3 dimensions. So then I would say, okay, tell me what it looks like in 4 dimensions. Yeah, all right.
Sure.
Yeah, it sounds great. All right, so in 4 dimensions, it would be packed granular, powder, icy, rocky. Basically, what is the quality of the terrain? That would be your 4th dimension. All right. So then your 5th dimension, like the temperature outside as you're skiing down the mountain. All right. So like any other variable that you could throw in, now you're adding a dimension, but they're not ones that you could perceive just based off of walking. Like I'm not going uphill or downhill anymore. Now I have to perceive the world around me. Right? But every single day we live in omnidimensional realities. Because you think 3 dimensions, length, width, and height, and I say, okay, temperature, you're like, oh crap. All right. So I mean, if I created a graph of this room, I mean, I guess I could just draw an open box, but I could also include temperature gradients as they work their way throughout the isotherms. Right. So maybe it's cooler, in the lower left-hand corner and warmer in the upper right-hand corner, right? But we would denote that with different colors and different representations. So then it's like, okay, well, how do we represent the change in temperature per change in volume? Like now it starts getting crazy. But if you could start to grasp the Jacobian, then you can get a sense of what's happening at least in the small scale. And then you can start branching out into other areas. Right? So that is, I was going to say, that's the best I got. In terms of an explanation, a practical explanation of the Jacobian, that's pretty much where it is. Because all of this, aside from the ninja at the bottom, is really just explaining that. There's some formulas here that I got from some website, I forget. Yeah. And then if your Jacobian, and so all of this, fun way of saying that if your Jacobian is an invertible matrix, then you could come up with a function that represents the behavior around your particular set of points. It would be an inverse function, right? But that's still not really what we're after here. Right? What we want to do is actually just determine the Jacobian matrix and then also determine what the Jacobian determinant would be. And again, the Jacobian is the same as the Jacobian determinant, right? Overusing a term. It's like one of those things. Like you invent a concept, go ahead and name it after yourself, and require everybody to refer to it that way, right? So Newton's, for example, like you come up with it, you can name it, right? So Jacobian. Sorry. Anyway, so we have a function of multiple variables. Y1 equals x1. Y2 equals 5x3. So we use x1, x2, x3 in lieu of x, y, z. So y is just something completely dependent on whatever our x1, 2, 3 are. Right? So it's not even considered to be part of the same realm as x1, 2, and 3. All right? So x1, 2, and 3 would be length, width, and height, for example. Those are your 3 dimensions. y1 would be some transformation of this function x1, all right, or the result of that transformation. And really everything in terms of an equation is a transformation, right? Because really if you graph y equals the sine of x, you're transforming a line on the x-axis from negative infinity to infinity to a sine wave. Right? The y values are the transformed values going from 0 to somewhere else. Right? That's all that's happening here. This is the result of the transformation. So what we do in order to create the Jacobian matrix is very simple. We just find every single partial derivative that can be found in terms of every variable that can exist. All right? So you can see the breakdown here. I have 4 y's, y1 through y4. So I could take a partial y1 with respect to, well, I have 3 x's, x1, 2, and 3. So I could say partial with respect to x1 of y1. All right, well, if I look at my breakdown here, these are my possibilities. Partial y1 with respect to x1. Okay, well, that's saying take the derivative where this is the variable. Okay, so that's just 1. Got it. Partial of this with respect to x2. Well, that would mean that this is treated as constant. Derivative of a constant is 0. Partial of this with respect to x3. This is treated as constant again because it doesn't involve an x3. Must be 0 also. Right. Function 2. Partial with respect to x1. There's no x1, so 0. Right? So that's where this is coming. Each row corresponds to a different equation. Partial with respect to x2, also 0 because there's no x2. But when I get the partial with respect to x3, now it's just 5. All right. So, and all it, I mean, subscripts aside, all it is power rule. It's 5x3 as a variable to the first power. Multiply power by coefficient, reduce the power by 1. All right. In y3, I don't have an x1, so partial with respect to x1. All of these are treated as constant. Get rid of them, 0. With respect to x2, the second term is treated as constant. That goes to 0, but this part I can take the derivative of. It becomes 8x sub 2 to the first power. And then with respect to x3, this first component is treated as constant, and this becomes just a negative 2. All right? And then y4, with respect to x1, a little dicier. We have a constant multiple. So I got to hang on to that, but the derivative of sine x sub 1 would be cosine x sub 1. With respect to x sub 2, there is no x sub 2, so 0. With respect to x sub 3, the sine x sub 1 becomes a constant multiplier of x sub 3 to the first power. It's weird to think that you're using a trig function as part of the power rule, but that's really what's happening. All right. So what I wanted to do is take this and show you how you find the Jacobian determinant. All right, aka again the Jacobian. Fun fact, you're just finding the determinant. All right, except your result will involve a function. Pick your favorite row and column. Oh, pick your favorite row. That should then lead you to the appropriate setup. So shorthand so you don't have to write it over a second time. The Jacobian of your function f. Coefficient of 1. Now you see here we would have 0, 5, 8x sub 2, negative 2, 0, and sine of x sub 1. All right. So, even beforehand, you should generally tend to recognize this, but like how are you going to use a shortcut rule, diagonal down minus diagonal up, when you have a 3 by 2 matrix? All right, so this is going to be no good. All right. I mean, you could try to use, if you want, you could try to do it again where you work across the top row, but then you're going to have a 2 by 1 matrix. The determinant of a 2 by 1 matrix is meaningless. All right, so not possible. All right, because when you're dealing with matrices, we know that in order to find the determinant, you would have to have a square matrix. All right, so you look at this and say, well, okay, well, where did that get us? Well, it got us to the idea that you could still get relevant information from the Jacobian matrix without necessarily having a Jacobian determinant to go along with it. All right. But if you can't get a Jacobian determinant, what you'll get is generally a relatively simple polynomial, or at least something of a polynomial form that'll give you a good sense of the goings on, I suppose, around that particular point, a designated point. All right. But what this will do is it just gives you basically an encoded way of describing the behavior of the graph. So the matrix itself is useful, although the determinant would be even better. So we move to the second one. Oh, I told you there'd be a typo. Find the behavior around 104. So I got to make my matrix out of this. Now I have y1, 2, and 3, and I have x1, 2, and 3. So this is going to be a 3 by 3 square matrix. So I know that at least I'll be able to attempt to find the determinant. It could be that the determinant's equal to 0, but that's for us to find out. All right, so my Jacobian matrix, I'm going to disregard the you know what, I was going to say disregard the variables, but I'm going to put them in it. All right, so we're looking at our first matrix, our first row, partial with respect to, and you could use the top as a model, partial with respect to x, 1, then x2, then x3. In my first equation, there is no x1, so the partial would be 0. There is an x2, its coefficient is 5, so its derivative would be 5. There is no x3, so its partial would be 0. In the second equation, there is an x1 term, so we'd be looking at 8x sub 1, but everything else zaps away. The second part, different story. I regret making this so narrow, and I'm locked out. The second part, we're looking at, well, the 4x sub 1 squared is going to go away, but I'm going to have a negative 2 sine x sub 2 x sub 3, but then multiplied by x sub 3. Put the 5 back in now. All right. And you can clean it up, but it's also not necessary. For the x sub 3, again, the 4x sub 1 squared is going to be gone. I'm going to have pretty much the same thing, except I'm going to have an x sub 2 at the end. And there's a 0 on top here. All right, so that part was a little juicy. Because I'm a fool. Thank you. I do appreciate how everybody sprung to my defense on that thing. No, you're not a fool. Well, you are a fool, but you're a great guy, so that's got to count for something. But thank you. So there's no x sub 1, so this zeroes out, the first term anyway. Derivative of it with respect to x sub 2 would be x sub 3. Derivative with respect to x sub 3 would be x sub 2. So now I just need the determinant of this. Dear Lord. We're going to be at this all night. Nah, it's not that bad. All right, because again, we got lots of zeros. And that's the thing when it comes to the Jacobian. I mean, very rarely are you going to see situations where each equation is in terms of each variable. Right? Because you got to imagine that some algebra was completed in order to streamline this a little bit before you get into the Jacobian process. Right? So substitution, combining like terms and things like that. Things would cancel away. Right? And when that happens, you do tend to get a lot of zeros. Right? But, just like the last one, the last one didn't work out, but this one, we still want to work across the top row. But it's the second entry in the top row. That's position 1, 2. So that's an odd position. So negative 5. And then we multiply that by diagonal down minus diagonal up. But I'll write it. So 8x sub 1. All this cosine stuff is wonderful, it's going to end up being irrelevant. Because diagonal down is going to give me an 8 sub 1 x sub 2. Diagonal up is going to give me 0. And so we end up with negative 40 x sub 1 x sub 2.
Why is it a negative 5?
Because the second entry is position 1, 2. So it's negative 1 to the 1 plus 2 power. So I'm going to highlight this part of it also, I guess. So you want to think about, well, what does that tell me? If the determinant of the Jacobian is greater than 0, orientation is preserved. In the transformation. If the Jacobian is negative, orientation is reversed. And the single most annoying one would be if the determinant of the Jacobian is equal to 0, possible extreme value. Which would tell me that it could be a max, could be a min, or maybe it's neither of them. But what we're getting at here is you have some sort of figure, three-dimensional figure, in 3 space that's moving along one pathway. And then if you have a Jacobian that's negative, its orientation is going to be reversed. So if you're moving on the high side of a surface, once you get to that point, you would then be moving on the low side. So it'd be more like, if I can do the twist, I need a narrower one. I can never do it. You know what I'm trying to do, though. Nope. Come on. Get it. One day I'll just actually bring one. Yeah, there we go. Kind of almost there. Yeah. All right, so when you're on the high side, you're now on the low side. If you're on the low side, you're transitioning to the high side. It's basically a Mobius strip. Right, so that's, I had to sacrifice an entire handout for that, but you know, for one strip of paper, one day I'll actually just remember to bring my manipulative and I won't have to deal with that, but I forgot, so here we are. All right, so we're at 104. 104 would be x sub 1, x sub 2, x sub 3. All right, so I can make a little note here that at 104, the Jacobian's determinant, that should be a J, is going to be equal to 0. So its behavior would be that it's a possible, a disgusting word, possible, extreme value. All right. It's kind of more important that you start to realize that we have the Jacobian as negative 40 x sub 1 x sub 2. What we're more importantly than testing it at a particular point, determining the behavior, what it's really giving me is a sense of extreme values in general. So now I know that anywhere that x of 1 or x of 2 is equal to 0, the determinant's going to be equal to 0. And so at any of those locations, anywhere along those, you're basically holding x of 1, x of 2 constant at 0. Anywhere along those pathways, you could be looking at extreme values, right? And so maybe it's all along the x equals 0 plane, that intersection, in which case maybe you have a ridge, and that ridge ends up being the maximum, so it could be something along those lines. All right, but it's starting to give you a sense of what these things might look like in 3 space, 4 space, 10 space, whatever. All right, because trying to make heads or tails out of this in higher dimensional space is really not easy.